Hello and welcome back to the continuation of the line integrals. In this video I'll carry on with some general properties of line integrals, maybe some simple closed curves, maybe Green's theorem, and some conditions for the line integral to be independent of the path. So, some general properties. Line integrals have properties which are analogous to those of ordinary integrals, so they don't differ real much, really. So, first off, the integral over k of p of x and y dx plus q of x and y dy is simply equal to the integral over k of p of x and y dx plus the integral over k of q of x and y dy. The second property is that the integral from a1b1 to a2b2 of p dx plus q dy is simply the negative integral from a to b2 to a1 b1 of the same integrand p dx plus q dy. Thus, reversal of the path of integration changes the sign of the line integral. Third property is that the integral from a1 b1 to a2 b2 of p dx plus q dy is equal to the integral from a1 b1 to a2 b2 of p dx plus q dy plus the integral from a3, it should be a3 b3 plus the integral from a3 b3 to a2 b2 of p dx plus q dy, where a3 b3 is another point on k. Similar properties hold for line integrals in space, multiple dimensions. Let's now continue with simple closed curves. So, what is a simple closed curve? Well, a simple closed curve is a closed curve which does not intersect itself anywhere. Mathematically, a curve in the xy plane is defined by the parametric equations x equals phi of t and y equals psi of t, where phi and psi are single valued and continuous in an interval t1 less or equal to t less or equal to t2. If phi of t1 equals phi of t2 and psi of t1 equals psi of t2, the curve is said to be closed. If phi of u equals phi of v and psi of u equals psi of v, only when u equals to v, except in the special case where u equals t1 and v equals t2, the curve is closed and does not intersect itself, and so is a simple closed curve. We shall also assume, unless otherwise stated, the phi and psi are piecewise differentiable in the interval t1 less than or equal to t less than or equal to t2. If a plane region has the property that any closed curve in it can be continuously shrunk to a point without leaving the region, then the region is called simply connected. Otherwise it is called multiply connected. As the parameter t varies from t1 to t2, the plane curve is described in a certain sense or direction. For curves in the xy plane, we arbitrarily describe this direction as positive or negative, according as a person traversing the curve in this direction with his head pointing in the positive z direction has the region enclosed by the curve, always towards his left or right respectively. If we look down upon a simple closed curve in the xy plane, this amounts to saying that traversal of the curve in the counterclockwise direction is taken as positive, while traversal in the clockwise direction is taken as negative. Let's now make a brief connection with Green's theorem in the plane. So let P, Q, the partial derivative of P with respect to y, and the partial derivative of Q with respect to x be single valued and continuous in a simply connected region R, bounded by a simple closed curve K. Then the integral with a little circle over K of P dx plus Q dy equals the double integral over R of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y dx dy, where this integral sign is used to emphasize that K is closed and that it is described in a positive direction. This theorem is also true for regions bounded by two or more closed curves. They're called multiply connected regions. So let's now talk about the conditions that need to be satisfied for a line integral to be independent of the path. So, theorem 1. A necessary and quite sufficient condition for the integral over k of p dx plus q dy to be independent of the path k joining any two given points in the region R is that in R the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x, where it is supposed that three partial derivatives are continuous in R. The condition is also the condition that p dx plus q dy is an exact differential. That is to say that there exists a function phi of x and y such that p dx plus q dy equals d phi. In such case, if the endpoint of curve k are x1, y1 and x2, y2, the value of the line integral is given by the integral from x1, y1 to x2, y2 of p dx plus q dy. That is equal to the integral from x1, y1 to x2, y2 d phi is equal to phi of x2, y2 minus phi of x1, y1. In particular, if this condition holds and k is closed, we have that x1 equals x2 and y1 equals y2, and then the integral over k of p dx plus q dy equals 0. these results can be extended to line integrals in space. Thus we have another theorem. Theorem 2. A necessary and sufficient condition for the integral over k of a1 dx plus a2 dy plus a3 dz to be independent of the path k joining any 2 points in the region R is that in R the partial derivative of a1 with respect to y is equal to the partial derivative of a2 with respect to x. Similarly, the partial derivative of a3 with respect to x is equal to the partial derivative of a1 with respect to z. And lastly, the partial derivative of a2 with respect to z is equal to the partial derivative of a3 with respect to y, where it is supposed that these partial derivatives are continuous in R. These results can be expressed concisely in terms of vectors. If A is equal to A1 in the I direction plus A2 in the J direction plus A3 in the K direction, the line integral can be written as the integral over K of A dotted with dr. And this condition is equivalent to the condition that the curl of A is equal to 0. If A represents a force field, say F, which acts on an object, the result is equivalent to the statement that the work done in moving the object from one point to another is independent of the path joining the 2 points, if and only if the curl of A is equal to 0. Such a force field is often called conservative. This condition is also the condition that a1 dx plus a2 dy plus a3 dz, or a dotted with dr, is an exact differential. That is, that there exists a function phi of x, y, and z such that a1 dx, a2 dy, a3 dz all added together equals d phi. In such case, if the endpoints of curve k are x1, y1, z1 and x2, y2, z2, the value of the line integral is given by the integral from x1, y1, z1 to x2, y2, z2 of a dotted with dr. This is equal to the integral from x1, y1, z1 to x2, y2, z2 d phi, which is equal to phi of x1, y1, z1 minus phi of x2, y2, z2. In particular, if k is closed and the curl is equal to 0, we have that the closed integral over k of a dotted with dr is equal to 0.